This lecture is an introduction to deterministic dynamic programming. DP is a method to solve optimization problems by decomposing the problem into stages, where each stage constitutes a subproblem to be solved. So we solve each subproblem independently, then we sew the various solutions together to come up with an overall solution to the overall problem. The optimal solution of one subproblem is used as an input to the next subproblem. This is the strategy then. Um, then the DP computations are recursive. We'll see that in the next few slides. So the key performance step here is decomposition. How do we decompose the problem into subproblems? In order to look at that decomposition, let's revisit the shortest path. So let's revisit the shortest path problem, looking at it from the perspective of dynamic programming, DP. Two important terms are necessary to identify in DP: stages and states. A stage is defined as a collection of states. Here in this slide we see 5 states. That's one state. That's one stage. Another stage 2, stage 3, stage 4, and stage 5. So there are 5 stages. Each stage consists of one or more states. For example, stage 1 has one state A, stage 2 have 3 states B, C, and D, stage 3 has 3 states E, F, and G, stage 4 has 2 states, state H and state I, and last stage has one state only, J. So if I tell you you're in stage 2, for example, then you could be in any one of those 3 states, B, C, or D. So the question is, how do we solve the problem of one stage and then sew the sub-solutions together for each stage to form a final overall solution to the DP problem? The key idea here is to compute the shortest distance to all the states of a stage and then use this information as an input to the immediately succeeding stage. For instance, if you are in stage 2, you could be in any one of these 3 states. I said state B or C or D, but where did you come and how did you come to state B? You came from stage 1 in state A. Okay. Before we go deeper into the DP solution to the shortest path problem, let's look at other approaches before we continue with the DP solution. One possible approach is to enumerate all the possible routes. In this case, there are 18 different routes for the previous problem, and this is called an exhaustive enumeration method. So this is you enumerate all possible routes from the start to the end, and then basically you select the shortest route. But this is definitely not a good approach for large networks where enumerating all possible routes from start to finish is sometimes computationally prohibitive. You cannot enumerate them. There are just too many of them. Just counting them is a problem. So it works for smaller problems, this exhaustive search approach or enumeration approach. Myopic policy is another approach, another strategy to find a solution, but it may not necessarily be optimal. And the myopic policy or short-sighted policy is usually, it says, starting and from the beginning, take the shortest path to the next route, and so on. And then basically you will get a route which is not necessarily optimal, but that's called sometimes a greedy also algorithm, myopic or greedy. And the last one is Dijkstra, which we studied the Dijkstra's algorithm, which we studied in the previous chapter. The DP solution approach is based on the following. The problem can be divided into stages, so that's the composition step, with a policy decision required at each stage. So the solution actually to the DP problem, we don't call it an optimal solution, but we call it a policy, maybe optimal policy. So what do you do if you are at a specific stage in a certain state? What's the action that you should do? What's the optimal move that you should do? And this is called a policy. Each stage has a number of states. We mentioned that already. So there are a bunch of states associated with a stage. The effect of the policy decision at each stage is to transform the current state into a state associated with the next stage. So basically, how do you move from one stage if you are to the next stage? If you are in a certain state in a stage, what's the optimal move? What's the best thing you do to get to the next stage? The solution procedure is designed to find an optimal policy for the overall problem, and not a solution, as I said. A policy, a prescription of the sequence of the optimal policy decision at each stage. Let's look at the shortest route problem, the previous one that we saw in a few slides earlier. And then we see here that there's stage one, and there's one state in stage one. And then there's stage two, and there are three states in stage two, state B, C, and D. So the question is, that's the first sub-problem I need to solve. How do I get from stage one to stage two? That's one problem. And then another sub-problem, how do I get from stage two to stage three? And the third sub-problem, how do I get from stage 3 to stage 4? And the fourth sub-problem, how do I get from stage 4 to stage 5? And I think the stage 5 was the last stage. So finding solutions to those four sub-problems and then being able to glue these four sub-solutions together will form an optimal policy for the overall problem using DP approach, obviously. Let's look at this sub-problem going from stage 1 to stage 2. The way we start, we say that if you are in state B in stage 2, how did you get to this point? Shortest distance to node B from stage 1 is definitely through state A. There's no other state. So node B can be reached from node A, and the shortest distance is 2. Now, there are no other solutions to this sub-problem because this is the only way you get to state B in stage 2 is through state A in stage 1, which is node A, and the cost is 2 or the distance is 2. Now, if you are in state C in stage 2, the shortest distance to C is also from stage 1 is also through node A or state A because it's the only state, and then the cost is 4. And finally, the shortest distance to state D or node D in stage 2 from stage 1 through state A, because it's the only state, I keep repeating that, in stage 1, and the shortest distance is 3. So the second sub-problem deals with moving from stage 2 to stage 3, and in this case stage 3 also has 3 states or terminal nodes, which we call them, or nodes. So states E, F, and G in stage 3. What is the shortest distance to state or node E? Well, it depends. It depends on what? It depends where you're coming from in stage 2. In stage 2, you could be coming to E from state B, or you could be coming to E from state C, or you could be coming to E from state D. We don't know. So node E can be reached from nodes B, C, and D. Let's call these nodes as I in general. So I are the various nodes in the previous stage, in stage 2, that can be reached to the current stage and the current state. Current stage here is 3, current state here is E, node E. Then the shortest distance to node E, here's the rule, is then the shortest distance to node E is equal to the shortest distance to node I. I was defined as either B, C, and D, all the nodes in the previous stage that can reach E. So the shortest distance to node I plus the distance from I to E. Okay, let's see those calculations in the next slide. So the shortest distance to node E is equal to the distance to node I plus the distance from I to E. That is, the shortest distance to node B. Now, if you're coming to node E from B, then the shortest distance to node B, now I equal to B, the shortest distance to node B is, and I find that actually from the solution of the first subproblem. If you recall, the shortest distance to B, and originally there was a path only from A to B, and it was only 2. So that was the shortest distance to node B. It was A to B, and the cost or the distance was 2, plus the distance from B to E, which is now 7, to get from B to E, because there is a path from B to E, as we said. Then the answer is 9. So the shortest distance to node B is 9 if you are coming from stage 2 in state B. But if you are coming from stage 2 in state C instead, then the shortest distance to node E is the shortest distance to node C. Now I is C, the shortest distance to node C, and recall again that the shortest distance to node C in subproblem 1, we were going from stage 1 to stage 2, it was 4. So we look, and that's how we're using the sub-solution from the previous problem to solve the next problem in this DP approach. Distance to node C, the shortest distance to node C, which was the only distance anyway, because there's only one path from A to C, and it was a path of 4, plus the distance from C to E, which is 3. Right here, it should be 3, the path from C to E. Also, another option that you could get to node E or state E in stage 3 is from stage 2 through state D. Okay, we're just enumerating all possible ways to get to state E in stage 3. And the last one was D. Now I equal to D, and the shortest distance to get to node D is, again, I get this number 3 from the solution or the sub-solution of the first subproblem. It was 3. That's the distance from A to D. If again you have to recall, you have to look at the solutions in the previous slide or two. 3. Now the distance from D to E would be 4, and then the total distance to get to node E is 7. Okay, and this 4 that we just saw is right here, the distance from D to E. Now, now we take the shortest distance to node E being the minimum of all these answers, 9, 7, and 9, which is 7. Okay, the shortest distance to node E is 7, and 7, that means you are coming from either C or D. Both have a cost of 7, as you see here. So, okay, so that means we'll see that later, that if you're the best thing to do is go to E. If you're at C, you go to E. If you're at D, you go to E. And that's how we read the sub solution actually. So let's look at the next sub problem, which is going to be solving the problem of going from stage 3 to stage 4, and we repeat the same exact calculations now. And mind you, keep in mind those minimum distances, because we're going to use them in the solution of the sub-solution of the next problem, which is going from stage 3 to stage 4. We're going to use all these numbers. Okay, so keep those in mind or handy. Yeah, sorry. We did not finish the solution of the second sum problem, stage 2 to 3, because I have to repeat the same thing that I did in the previous two slides. I have to repeat that for point F and point G. What we just did in the previous slide, it was that we found the sub-solution to this problem from stage 2 to stage 3, assuming that we are in state E. But now let's assume we are in state. Let's assume that we are in state F. So if we are in state F, we have to repeat the same calculations like we did for state E. And how did you come to state F? In stage 3, you could be coming to state F in stage 3 from stage 2 from 3 possible states. You could be coming from state or from node B, state C, and state D. Okay, now a shortest distance to node F, or not yet, or the distance to node F is the shortest distance to node B, which is 2. Again, from A to B it was 2, plus the distance from B to F, which is 4. Here's the 4. Here's the distance from B to F, and thus I add here 4, and then thus the distance is 6. So the distance to F from B is 6. The distance to F from C is 4, which is the distance from A to C, the solution of the first subproblem, and then from C to F is 2, this 2 right here, C to F, and then the answer is 6. Similarly, the shortest distance to D from the solution of the first subproblem is 3, and then a plus 1, which is the distance from D to F. D to F, this is 1, and thus it's 4. So the shortest distance, now we say the shortest distance to F is the minimum of all of these distances, which is 664, which is 4, and thus if this is the minimum distance, so the solution to this subproblem is, if you want to come to F, it's best thing you come from D. Okay, and we're going to see how to use these also sub-solutions later, but again, keep that in mind. So the next slide is going to be the same exact calculations, but I'm repeating it for for state or node G. If you're in stage 3 in state G, you could be coming to that from stage 2 in state B or state C or state D. The shortest distance to state G is equal to the shortest distance to state B plus the distance from B to G, which is 6. So the distance from A to B is 2 plus 6 equal to 8. Similarly, the shortest distance to C is 4 plus the distance from C to F, C to G, which is this 4, plus 4 equal to 8. Similarly, 3 plus 5 equal to 8, which is this 5 is the distance from what? From D to G. And then we take the minimum of those 3, and in this case there's a tie. They're all 3. You could be coming from anywhere, is fine if you are in state G. So the next slide, now we're going to start a new sub-problem, and that's going from stage 3 to stage 4. We do the same thing. The terminal nodes or the states of stage 4 are 2 now, H and I, and the shortest distance to H is you'll be coming from either E or F, right? or G. So the shortest distance to E is read from the previous slide, those minimum thing, and that was, it should be read as 7 plus the distance from E to H is 1, and thus the answer is 8. The shortest distance to F plus the distance from F to H, and the shortest distance to F is also read from the previous sub-solution. This is the minimum thing, and it was supposed to be 4 plus the distance from F to H, which is 6. Thus the distance is 10. Finally, we have 8, which is the shortest distance to get the sub-solution of the second sub-problem, which we want to get to, what's the shortest distance to get to point G, and then distance from point G to point H, which is 3, and thus 8 plus 3 is 11. Now, the shortest distance to get to H is the minimum of all these 3, 8, and 10, and 11, and thus the minimum is 8. So now, in the next sub-problem that we're going to be solving, which how to get from stage 4 to stage 5, we're going to use this number as the part of the solution. And again, when I say what's the shortest distance to get to H, it will be number 8. And those are similar to those numbers that I'm getting here, the first numbers. Okay, so what do you think the next slide is going to be? It's going to be the same exact calculations, except that it's done for or performed for I. So what if you are in stage 4, but in state I, not in state H, what do you do? So we repeat these calculations, and we get, how do we get to I? We can get to I from 3 possible states, E, F, and G again, and then the shortest distance to E, and that's the same number, by the way, that we used in the previous slide, because the shortest distance to E is 7, plus the distance. Now this will differ, the distance from E to I. E to I is 4, and thus we get 11. Similarly, we get the shortest distance to F is 4, plus the distance from F to I is 3, and thus the answer is 7. And then the shortest distance to G, it's 3, and then the distance, the shortest distance to G is 8, that's from the previous sub-problem, plus 3, this 3 is the shortest distance from, or the distance from G to I, which is 3, and thus the answer is 11. Now the shortest distance to node I becomes minimum of all these 3, 11, 7, and 11, thus it's 7. Now we're done with the solution of the third sub-problem. Now we go to the last sub-problem, which is going with the last sub-problem is going from stage 4 to stage 5, and in this case stage 5 has only a single state. So how do you get to J? We get to J either from H or from I. So the shortest distance to get, or the distance to get to J is the shortest distance to get to H, which is taken from the previous sub-problem solution, which was 8, plus the distance from H to J is 3, and thus the answer is 11. And then the shortest distance to get to I is 7, plus the distance to get from I to J is 4, and then we have the total answer is 11. And there are no other states, so there's only one slide that have the solution for this fourth sub-problem, I guess. And then you have the shortest distance to J is the minimum of those two, which is 11. So this is the final optimal solution. This is how we read it from the policy, as I told you, not a solution. And we go backwards in this case, and starting from the previous slide, it says the shortest distance to get to J was 11, and 11 can be reached from, and the answer is either from H or from I. 11 because there was a tie, then you have to check that slide, and 11 was due to you're coming either from H or from I, both have a score of 11. So that's why you have those two routes are bolded anyway. So both are part of the optimal solution. There are alternative optimal solutions. So let's take one of them. Let's say we're coming from I. So this is the So j to I backtrack as I said, that's how I read the optimal solution. And then now if you are at I, what's the optimal solution? So I need to look at the slide that has to do with node I, okay, which is 2 slides back, and it says the minimum shortest distance to get to node I was the minimum of 11, 7, and 11. You know, you have to look at that slide. As I said, it's 2 slides back. And then the answer was 7. And 7 is the answer for coming from node F. Okay, so then I have to go to node F, and that's how I know that I will go to node F and no other node. Now, once I'm at node F, what I have to do, I have to go to the slide that has node F calculations. Okay, and that I'm trying to go back. The shortest distance to node F is min 664, which is equal to 4, and this 4 is by coming from node D. So that means I have to go to node D, or I'm coming from node D actually. That's how I read it. And when I'm at node D, then I have to look at where am I coming from. In this case, actually, there's only one option. You have to be coming from node A because it's the only starting node, and then you go. So the optimal path, one of them at least, because there's an alternative optimal path. One of them is ADG. Sorry, it's ADFIJ. Now you want to try. There are alternative paths. You want to try to, if you go through H, try to get that solution now. J to H, from H you're coming from E, from E you can be coming from 2 different places. Again, there's a third alternative solution in this case, and then let's say you came from C instead of D, then you are coming from A either ways. Try to get that by reading the various solution slides to get the same answer. The previous calculations were performed using a forward recursion. That's what we call it. So we start from stage 1 all the way to stage n. In that case, n was 5 in our previous problem, but you know, there are n stages in general, and there's are states within each stage, different states within each stage. So in the forward recursion, we start in stage 1 and we progress towards the end or the final stage or node. They can be placed, these calculations can be placed in tables instead of doing it the way we did it in the previous few slides, just to make it easier to follow. And this is the slide showing those kinds of calculations in this slide and the next slide. So in this case, if a problem has n stages, our previous problem had, shortest path problem had 5 stages. So we build n minus 1, in this case 4, 5 minus 1 is 4 tables in which we try to find the solution using the forward recursion. And you can see here the first table is from stage 1. It doesn't say stage, it should stay stage. Let me. Okay, so we go stage stage 1 to stage 2. So it's from 2. So here from A to B, from A to C, from A to D. So we read this is 2. Okay, and here's from. Okay, from stage 1 to stage 2, from state A in stage 1 to state B in stage 2. Now we put these distances, and those are taken exactly from the network, and there's a number above the arrow that connects A to B, and that number was 2. So you can check that out by looking at the previous slides. So we put that 2. And remember here, or that there was no other node or no other state in stage 1 except A, so there's only one, and then you can go to B, and the cost is 2. You can go to C, and the cost is 4. You can go to D, and the cost is 3. So all of these distance from A to B, A to C, A to D. And then looking at now across the row, after I filled the column, look across the row, and there is no other option but A. This is the only state in stage 1. So and then I just take the minimums. In this case, the minimum of 2 is 2, the minimum of 4 is 4, the minimum of 3 is 3. So this first table is kind of trivial because there was only one state in stage 1. Now that's the solution of the first subproblem going from stage 1 to 2. Now the other subproblem, the second subproblem going from stage 2 to stage 3, and look at here. Now we put all the states in stage 2, B, C, and D. Basically, those are the ones here. They were copied there. Okay. And now we have stage 3. These are the various states in stage 3. Now, I will fill up column by column, and starting from stage 2 to stage 3 and state B in stage 2, going from B to E. B to E, what's the cost of, what's the minimal cost or the smallest cost to get to state B in stage 2 plus the cost to go, we call it the cost to go from B to E, which is 7. And that 7 is read from the arrow or the link that links node B to E in the network. But this number, the minimum cost for B, is read from the previous table, and that's where you see the arrow here going from, I just read over the minimum. So point B, I go to point B, the minimum is 2, I just copy it. And obviously that 2 is copied in all the entries in that column, because that's the minimum cost to get to B. But this number will change, and that's the number on the arrow from B to E, this is the number on the arrow from B to F, and this is the number on the arrow from B to G. So it becomes much easier to populate these their numbers in the table format versus what I did in the previous slides, a slide for each one of these. So this is the way we should do it, actually, using those tables, dynamic DP tables, instead of the slides that I used in the beginning of the lecture. But I did that just to show you that how what do they really mean. So similarly, then I can fill now column C, the second column, and this number actually 4 is used in all the first numbers. What's the minimum cost to get to C? And that's, I find it from the previous table. This number 4, it's copied everywhere here. And then this is the number on the arrow that goes from C to E. The 2 is the distance from C to F, and 4 is distance from C to G. And similarly, this is filled. So what is this number, by the way, you think? There's nothing but coming from this table right here. And then this is the distance on the arrow from D to E, arrow from D to F, arrow from D to G. Now, after I finish filling all the columns, now I take it row by row. I look at the minimum in the row. So what's the minimum of 9, 7, and 7? It's 7. What's the minimum of 6, 6, and 4? It's 4, and so on. So I get those minimums. So now, when I use the answers in the next subproblem, I will say, what's the minimum distance to get to node E? It is 7. What's the minimum distance to get to node F? It is 4, and so on. So now, then the next table, the next DP table, is the solution to the subproblem of going from stage 3 to stage 4. And again, those are the states in stage 3, E, F, and G, which obviously are the same ones here. And then those are the only 2 states in stage 4, H and I, and the calculations are repeated. So this 7 in both numbers is copied from here. This 4 is copied from here, and this 8 is copied from here. and then the next number here, 7 plus 1, this one is again the number on the arrow that links E to H. This is the number on the arrow that links E to I, and this is the number on the arrow that links G to I. And then you read across the row to find the minimum, and you get your 8 and 7. The next tableau, or table, sorry, DP table, is for the last stage. As I told you, if there are 5 stages, n stages, and then I will use n-1 tables, that means 5 stages require 4 tables, and this is the fourth table. And from stage 4 to stage 5, and there's only one state in stage 5, and there are 2 states in stage 4, and then the same thing. This 8 is taken from the previous table here, and this 7 is taken from the previous table here, and then obviously this 3 is the distance from node H to node J taken from the network, and this is the distance from node I to node J taken from the network, and then minimum is 11. So basically, this is how I populate the DP tables, and I can do it on a single sheet instead of using multiple sheets as I did in the previous problem. So now, how do I read the solution from the previous slide or from these tables? The only thing I added to the tables in the previous slide is this column, and this column, and this column, and this column. The rest are the same, and the column says where did the minimum occur, because I used the minimum of 2, which is here. Where did the minimum occur? The minimum occurred, and here, because there's only one state, the minimum occurred at that state. So 2 came from state A, and this 4, which came from here, came from state A. Similarly, this 3 came from this 3, which belongs to state A. So that's trivial because there was only one state in stage 1. The next table here, the 7 came from where? 7, 7, 9. So it came from both. So either from state C or state D, and thus I write here C, comma D. Both are fine. So the optimal answer, or the minimum answer, came from those 2 states. The 4 came from only one state, and thus I circled this 4, 6, 6. No, 4. It came from state D, and thus it's D. The 8 came from all of them, so it came from B, C, or D. So B, C, or D. Okay, and I'm going to use these to read the optimal solution in a second. And then 8, minimum is 8. This came only from E. And then 7, this came from 11, 7's 11, then this is the 7, and it came from F, from node or state F. Finally, we have 11, it came from either H or I, either H of I. Now, how do I read the solution? I can read it as follows. Okay, J, you either can come from state H or I. So both, you can bold that connection between HJ or IJ, same thing. So because we look at J, you're coming from either H or I. So we pick one, obviously, because there's alternative optimal solution. So let's say I picked I. So now I go to I here. Where are you coming from? F. So I go to F. Where are you coming from? D. So I pick D. Where are you coming from? A. And thus this is the optimal route. This could change if I have picked H instead of I, and then this will allow me to go from H to J. So if you picked H, then you're coming from E, and you're coming from either C or D, and either C or D, you're coming anyway from A. And that's the alternative route 2 in that case. Okay, so the formal DP equation, recursive equation to use in solving these DP problems is shown here. And let's look at the pieces. What is xi? It says fi of xi is the shortest distance to node xi. So xi at stage I. So we call xi the state of the system at stage I. That is, x of 1, let's say, is the state of the system at stage 1 or in stage 1. In the previous problem, what was it? It was only one state actually, and it was A. So x of 1 is A. How about x of 2? The states or the state of the system in stage 2, that could be multiple answers because the state of the system in stage 2 was states B, C, or D, and so on. So then the cost that we're trying to minimize or find is the cost to get to xi be the shortest distance to node I at stage I. So that's the cost to get to I at stage I, and then plus the distance to get from xi minus 1 to xi. So that's from state in stage x minus 1 to the state in stage xi. So we're going from stage xi minus 1 to stage I. Okay, so this is computed as follows. Minimum over all possible paths of going the distance from stage I minus 1 to stage I, plus the cost to the of stage x minus 1. Okay, so that's what we call the cost to go, and then the cost from this stage to that stage, and then the cost to go. Anyway, this is the formal representation of the DP recursive equation that we use, and which we used actually in building those tables that we've seen in the previous couple of slides. This is a very important principle, and it's basically the whole DP theory is built upon this principle. It's called the Bellman principle. A guy called Bellman came up with this principle of optimality. At any stage, at any stage, future decisions of the remaining stages will constitute an optimal policy, regardless of the policy used in the previous stages. Basically, the way to move forward, you follow the optimal policy, regardless of how did you get to that stages. That's all it's saying. That imagine that you woke up and you find yourself you are at a certain state in a certain stage. We don't know how did you get there. But moving forward to get from that point to the end, you follow the optimal policy. Okay, so that's what it says. Backward recursion, as I said, there's the forward recursion and the backward recursion. What we've been using so far is the forward recursion, but really in DP, backward recursion is much more popular than forward recursion, and that's backward recursion works by starting at the end and going back to the beginning rather than starting at the beginning and moving forward towards the end. So all these tables that you've seen to solve the shortest route problem that we've solved going forward from stage 1 to stage n, and now we're going to do it using backward recursion going from stage n back to stage 1. And so now solving the same problem but using backward recursion instead. So you can see here that the tables, there are still 4 of them, so it's n minus 1, n being the total number of stages in the problem. So you build n minus 1 tables, and that will be 4 tables, 5 minus 1, 1, 2, 3, 4 tables. However, the tables you start from going from stage 4 to stage 5 instead of going, from stage 1 to stage 2. That was the first table. If you remember, if you look at the previous slides for the forward recursion for these tables. So here we have stage 5 instead of stage 1, and then so now we're going from stage 4 to stage 5. Okay, so from 2 becomes this way, and now we're using more of the formal DP recursive equation, and look at this, it's x4. What are the states in stage 4? X4 could be H, X4 could be I, and this is X5. What are the states in stage 5? There was only one state, J. So now we're going from H to J in a way, and basically and this is the recursive equation, by the way, you know, whether the cost from j and on, there's no cost from j and on because j is the last node, and that's it's 0, that's the cost to go. No, that's actually the cost from j and on. But where this 3? This 3 is only the cost from h to j is 3, and then you end up with 3. There are no other states in stage 5, so there's only one column. And then I can do the same thing. From I to j is 4. From j and on, there's nothing, so it's 0. So that's f5 of x5 is 0 always. And this is the d from x4 to x5, from a state in stage 4 to a state in stage 5. But the only state in stage 5 is j, but there are two states in stage 4, h and I, and thus there are two numbers, 3 and 4. We take the minimum across the row just like we did with the forward recursion, and the minimum here is only one number anyway, so it's 3. There's only one number here, so it's 4. And this is coming from j. This 3 is coming from this 3, which is coming from j. So x star 5, you can see here the optimal state in stage 5 is j. Okay, there, and same thing is here. So let's go to the next table, and here now we're going from stage 3 to stage 4. So I put here stage 3 and I put here stage 4 states, and in this case these are h and I, so h and I, and these are e, f, and g. Mind you, here this is x4, states in stage 3, x3, and states in stage 4 is x4 formally. So x3 could be e, x3 could be f, and x3 could be g, and so on. Now here's the recursion. It says 1, the cost dx3 x4, the distance or the cost from stage 3 to stage 4, actually a state in stage 3 to state in stage 4, stage 3 to stage 4, and that's the distance just to go from e to h is 1. The distance to go from f to h is 6. The distance to go from g to h is 3. But this 3, which is the cost to go, that's f4 of x4, and you get this from here, f4 of x4. So this should say that the f4 of x4 is right here. F4 of x4 is 3. Yeah, sure. F4 of x4 is 3. Given that obviously x4 is h, so I look at h, x4 is h, then this f4 of x4 is 3. And if f4 is I, then f4 of x4, f4 of I, then I look at this, it's 4. Then I take the minimums, and then obviously this minimum 4 occurred from h, so I write x4 star is the h, and this minimum 7 occurred at here at I, so x4 star is I, and similarly this is h. Now in the third table, going from stage 2 to stage 3, those are the x2s, those are the x3s, and obviously to go from b to e is 7, plus what's x3, f3 of x3. If x3 is b, x3 is b, x3 is x3 is e, x3 is e, so f3 of x3 is 4, so that's this 4. But again, you copy it all the way in the same column because it's not going to change. Similarly, f3 of x3, if x3 is f, x3 is f, it's 7, so it's copied here. And then f3 of x3, if x3 is g, then g, f3 of x3, if x3 is g, then it becomes here 6 to copy it all the way. And those numbers are nothing but distances in this case, which is this x2, dx2, x3. So that means what's the distance from b to g, and that's thread from the network on the arrow connecting b to g, it's 6, and so on. Then you take the minimums, and then that's the same thing, repetition. And thus, of course, the last stage here, the last DP table is from stage 1 to stage 2. Stage 1 has only one state A, stage 2 has 3 states B, C, and D. It's You do that and you are done. A popular application of using the DP technique is the knapsack problem. The knapsack problem says that there's a thief who broke into a house and they want to steal stuff and fill it in his knapsack. A knapsack is a backpack, and he want to fill as much as possible into his knapsack or backpack. He has a limited capacity knapsack. That means it doesn't fit more than a certain amount of weight or volume, and that limit is W. Okay, in weight or volume. Let's say it's in weight. So you cannot put more than W stuff total weight into it. And in this house there are various items or item types that they can or he can steal from. And there's item type A, let's say maybe let's say chandeliers, and each chandelier weighs a WA weight, and it has a value of RA. So that type, so one chandelier weighs WA and has a value of RA. And another type of items he can steal from, let's say forks. This house has golden forks, and each fork weighs WB and has a reward or has a value, or he can sell it for RB, and so on. So there are basically N type items, and each one of these items have a weight and has a reward, the weight W or a cost W, and the reward RA. Okay, so that's the basic knapsack problem. So it's very easy to formulate the knapsack problem. There are N object types. Each weighs W1 through Wn, and each has a reward or a value or a profit of R1 through Rn. The capacity of the knapsack is a limited capacity of W. Okay, so actually the decision variables here that I want to find how many of each type of item to put in the knapsack, and that will be M1 through Mn, and M1 could be 0 because you could pack nothing of that type, or M1 could be 2 or 3 or 7 if you want to pack 7 items of that type. So you want to maximize MIRI, MI the decision variable, how many to pack of type I, and the reward of each will be Ri, the sum over N. And so maximize the sum of MIRI, and then subject to the sum of MIWI should be less than or equal the total allowed weight W. Okay, so obviously MI's are larger than 0, non-negative or equal to 0, non-negativity constraint, and they're integers in this case because you can't take half an item. And I is between 1 and n. So the way we solve this problem actually using dynamic programming is what we're going to see. As we have seen from the first DP application, which was a shortest route problem, in order to solve a DP problem, I need to define two things: stages and states within a stage. So for me to solve the knapsack problem, I need to define these two things before I proceed with the solution. So the stages for a knapsack are the different number of types. So there are n different types of items to be chosen from. Then there would be n different stages. The states within the different stages is a little bit different or difficult to define in the knapsack, not as it was in the shortest route problem. So pay a little bit of attention here. It says a state at stage I is represented by xi. So the states at stage I, where xi, so the state xi is defined as follows: xi is the state of stage I is the state of stage I, or the state in stage I, is defined as the total weight assigned to stages I plus 1, all the way till the end n. Again, the states of stage I is defined by the weight reserved or assigned for stages I plus 1, all the way until n. We will see what's the meaning of that in the next few slides when we solve a problem. But keep that in mind then, how it is defined. And finally, the alternatives for this particular problem define or represent the number of items that can be carried. So these are actually the decision to be made. Here's a graph representation of the knapsack problem, and it's saying that you could be carrying 0 items from stage 1, that means nothing of item type 1, and then go to if you select one item from type 1, then you go as if you're going in the graph this way, or if you select several items, you go that way, and so on. Really, it's not very important to visualize the knapsack problem as a shortest route problem, maybe. But here's what's we're showing. This slide is showing the network representation of the knapsack problem. Here's an example, small knapsack problem that shows us how to apply the DP algorithm to solve a knapsack problem. And it says there's a vessel or a ship that has a 4-ton capacity, that it cannot hold more than 4 tons of load in total. And there are 3 different items. Item type 1, it weighs 2 tons, and the reward for carrying or transporting this item, a single item, for 31. Obviously, if you transport 2 items of type 1, then you will get a reward of 62, double that amount. There are another type of items, item 2, that has a weight of 3 tons, and the reward on that is 47 per item. And there's a third type which has a weight of 1 and has a reward of 14. And obviously, if you carry 2 of these, you'll get a reward of double the 14, which is 28, and so on. Okay, so the question is, how many items of each type should we carry to maximize the benefit or the reward of this vessel? So we're going to solve this knapsack problem using a backward recursion, and let's define actually first of all the stages and states and the alternatives for this knapsack problem. There are 3 types of items, which means there are 3 stages, and if there are 3 stages, it means that I need to build n-1 tables, DP tables, which is 3 minus 2 is 2 tables. 3 minus 1 is 2 tables. Stage 1 has 3 alternatives. M1 equal, that means M1 equal to 0. Don't pick anything of type 1, or pick 1 item of type 1, or pick 2 items of type 1. That's it. Why don't we have M1 could be equal to 3? Because the capacity of the ship, which is 4, will be exceeded, because the weight of that item is 2. So the maximum you can hold is 2, and thus M1 can take values of 0, 1, and 2. While Stage 2 or item type 2 has two alternatives only, either 0 or 1, because the weight of type 2 was 3, so you can either hold no items of that type or only a maximum of one item. So thus M2 is 0 and 1. Finally, in stage 3, we have 5 alternatives because the weight of that item is 1, item type 3, so you can hold no item of that type, so that's 0, M3 equal to 0, or 1, or 2, or 3, or 4. So that was as far as the alternatives are. So there are then, as I said, 3 stages, and the alternatives M1, M2, M3, I enumerated them. And finally we have the states that we call them XI, stage X1 and X2 and X3 for the various 3 stages. So if we're going to solve this problem using backward recursion, we're going to build this table first, going from X3, and then we have here M3. The various alternatives are M3 could be 0, 1, 2, 3, 4, what I just mentioned a second ago, and the states. So we put here the alternatives, and then we put here the states for stage 3. Okay, so the state X3 is defined as the capacity reserved for state 3 and on. By definition, it says Xi, the capacity for stage I plus 1 all the way to n. So from stage I and on. In this case, for X3, from stage 3 and on. But there's nothing after stage 3, so there's just stage 3. Then X3 means that the capacity is reserved for X3. So what are the possible states for the capacity reserved for X3, or the capacity remaining for X3? That means what happens in the first 2 stages, stages 1 and 2, could be that all the capacity has been used by item types 1 and 2, and there are no space left for any item from type 3, and that's the situation. That's the state when X3 equal to 0. Or it could be a situation where I'm in stage 3, I'm selecting items of type 3, and I have already used up all my space for items 1 and I haven't used any space for items 1 and 2, and thus the free capacity remains at 4. So that means X3 could take any values between 0 and 4. So if X3 can be between 0 and 4, and M3 can be between 0 and 4 also, then what? Let's start populating the first entry here in the table. It says that obviously, look at the recursion equation, the DP recursive equation says F3 of X3 equal R3 M3 are the reward for the third type times the alternatives that you select for the third type, that's a decision variable, equal or plus stage 4 reward. That means the cost after or the cost after stage 3, which is 0 in this case. There's nothing after stage 3. So 14M, 14 is the reward for stage 3, and M is the alternative. And F4 of X4, there's no X4, and that's why it's at 0. So it's really 14 times M3 here initially. And then if you basically select no items of type 3, then you get a value of 0, and plus F4 of X4, which is 0. So it's 14 times 0 is 0 plus F4 of X4, because there's no X4, there's no stage 4, then it's 0 altogether. Obviously here it says no, nothing, because it says here that the state is 0. There's no space left in the knapsack, and then you cannot decide to put or pick one item of type 1 because there is no space. Okay, so that's why this doesn't exist, obviously, for M3 equal to 2 and so on. So I'll get back to these, but let me go over to this. When X3 is 1, that means there's 1 ton available left for stages 3 and on, but there's nothing after stage 3 as we agreed, so that means for stage 3, and you decided to select 0, then it's basically, even though there's a space left for you to select from type 3 items, but you chose not to, that means the value is 0. 14 times M3 is 0, 0. 14 times 0 is 0, plus F4 of X4 is 0, so it's 0. Well, look at here, when X3 is 1 and you you decide to select one item of type 1, and then the answer is 14. It's basically 14 times 1 is 14 plus 0, 14, and so on. Okay, when X3 equal to 2, then this would be 0 if you didn't select anything. M3 is 0, 14 if M3 is 1, and 28 if M3 is 2. So it's basically 14 times M3, which is 2, becomes 28 plus 0. And you cannot select more than that because you don't have the right capacity, so dash dash. And similarly, this whole thing. And now we go back here, F3 of X3 equal the max. So we take the max because we're maximizing in this case. Unlike the earlier problem, the shortest route method, which we were taking the min, we were minimizing, so we took the minimum of the row. Now we're taking the maximum of the row because we're just maximizing the value of the knapsack. That's the only thing. If we're minimizing it, then we'll take the min. So here we take the 0 because there's only one 0. There's only 0 in this row. The max is 14, the max is 28, the max is 42, and the max is 56. The max occurred at M3 star is, what's the best alternative to do? 0 occurred when M3 is 0, 14 occurred when M3 is 1, and thus M3 star is 1, and so on. So 0, 1, 2, 3, 4. The next table, the next stage, so the next stage we have, we list X2, the state of stage 2, and M2, the alternatives in stage 2. The alternatives were already decided for stage 2 because the weight of 2 was, what was it? The weight for item 2 was 2. Then we decided that we need to have we can only take a maximum of 2 items of type 2, and thus I'm sorry, it was 3 actually, and we can take the most of 1 item of type 2 because the weight was 3, and thus M2 could only take value of 0 and 1. Okay, now X2, what values can X2 take? X2, the state of stage 2, we said by definition the state of stage 2 or the state of stage I is the weight or capacity remaining for stages I and on. I means 2 and 3, and that's it. So 2 and 3. What possible values can X2 take, which is the capacity remaining for stages 2 and 3? That would be 0, because it cannot be negative, obviously, in all these problems, but it could be 0 because you have already used all the space for item 1, and you have already used all the 4 tons available by packing item 1 only type, and you are left with no space for items 2 and 3, and thus X2 could be 0. Or it could be on the other hand, or the other extreme, that you have not used up any space from item type 1. You took 0 of that, so, and which means that all the 4 tons are still available and remaining for stages or for types 2 and 3, and thus it's 4. So that means the knapsack is still empty in this particular situation, where when x2 equal to 0, the knapsack is completely full already, and before you even have started packing in stages 2 and obviously 3. So, but all these are the possible values that that x2 can take. So now we fill the rest of the table. That if x2 is 0, that means it's already full. How much can you take? I can take, yes, I can take 0, m2 equal to 0, which value of 0, so 47 times m2 plus f3 of x3, 0 plus 0, and this 0 is coming from f3 of x3. f3 of x3 means if x2 is 0 and m2 is 0, what would x3 be? And it's here you have to be careful. The relationship between x2 and x3 would be x3 equals x2 minus 3m2, 3 being the weight. So x3 equals x2 minus 3 m2. So which means if x2 is 0 and m2 is 0, so 0 minus 0 is 0, and x3 is 0, so I go and I check. x3 is 0, and f3 of x3 is 0, and this 0 is really coming from here. What if x2 was 1 and m2 was 0, so we decided to select 0 of type 2, which means 47 times 0 is 0, plus f3 of x3, which is this 14 anyway. Where did it come from? Now, since I use the same equation here, since x2 now is 1 and m2 is is still 0, 3 times 0 is 0, so the total is 1. Then I'm going to look at this one, and I'll take f3 of x3 to be equal to 14, and so on. So this way I will populate the rest of the table, and then I get the maxes along the rows, and obviously where does this max occur? For instance, this 14 occurred only when m2 is 0, so I guess m2 star is 0. And here, let's say this example, this 47, the max occurred here when m2 is 1, so then that's why m2 star is 1. Okay, so the next thing, so the next DP table would be stage 1, and I'm not sure if I said earlier in this lecture that I need n-1 DP tables to solve the knapsack problem. No, if I did, I was mistaken. We need n tables for the n stages to solve the knapsack problem. So if we have 3 different types of items, like in this problem, then we need 3 different tables. And remember that this table here on top is a repetition of the same table in the previous slide. I just put it here so that I can use it to fill to fill some numbers in the third table. Okay, so now then this is really our third table, which is stage 1, because I'm going backward. And the important thing here is to define x1. x1 is the capacity left for stages 1, 2, and 3. So that's it. And in this particular case, this slide is wrong. So be careful when you look at the slides that I have posted on Moodle for you, the PowerPoint slides. This shouldn't exist actually, because the only possibility for x1 to have is 4. Why? Because in the beginning you haven't used up any space yet for your in the knapsack. So it says the capacity left for stages 1, 2, and 3. So those are the only stages. So the knapsack capacity is still fully available. So it's still empty, and thus the capacity is only 4. So that means in this table, stage 1, X1 only have one option, which is 4, one state. However, the M1 is, as we agreed on earlier, it's M1 equals 0, 1, and 2. So remember that in this stage 1 table, we only need this one row for X1 equal to 4. Now, how do you fill it up? So it says if X1 equal to 4, but you chose not to select any item from type 1, that means M1 equal to 0. Thus, the benefit would be 0, and that's taken obviously from this recursive equation, M1 R1, but okay, 31 M1, but 31 times 0 is 0, plus F2 X2. Now, here's the thing. We need to find out the value of F2 of X2. But then I need to define what is X2. Similar to what I did in the previous slide, X2 becomes X1 minus, this time, 2 M1. So if X1 is 4, M1 is 0, so 4 minus 2 times 0 is 0, so 4 minus 0 is 4. So I look at 4 in the previous table, and then it is F2 X2 is 61. So this is plus 61. And the similar things are for this 28. It's a result of X1 being 4, but M1 being 1, and thus 4 minus 2 times 1, so 4 minus 2 is 2. So I look at the 2 here, and the answer is 28, so I use that 28 here. Okay, so now how do I read the answer? Now I read the optimal answer for this knapsack problem as follows. From stage 1, M star 1 equals to 2. So I look at the final table and it says M star 1 equals to 2. That's in the previous slide. So that means M star. Since M1 star equal to 2, then now I use the equation that I've used, X2 equal X1 minus 2 M2. Now I use the opposite. It says, well, X2 equal X1, which is X1, which is 4, minus 2 times M2, and M2 is 2. 2 times M2 is 2 times 2 is 4, so 4 minus 4 is 0. Okay? Obviously, the 4 that I just get is once I read M1 star is 2 from the previous slide in that table that has one row only, the X1 in there was 4 already, so I know that it's 4 minus 2 times 2 is 0. So that means from stage 2, I read that if X2 is 0, because I know X2 is 0 here, I look at X2 in the previous table. X2 is 0. I find that M2 star is 0 in that case. Since M2 star is 0, then X3, which is X2 minus 3 M2, then X2 is, we said X2 is what? Is 0. 0 minus 3 times M2, 3 times M2 is 0, 3 times 0 is 0, so the whole thing is 0. Then I will look at basically the first table in the backward recursion. I look at it and I see that that when X3 is 0, then M3 star is also 0. So the answer is 0 for M3, pick and 0 for M2, and only pick 2 of this type, M1.